Hello everyone, my name is Haitham. I'm very glad to introduce our work toward 3D human pose construction using Wi-Fi. This is a joint work with my lab mates, collaborators, and advisor from State University of New York at Buffalo. As we know, in the comics, the Superman can see through the walls using his X-ray eyes. But is it achievable in the real world? In this paper, we propose our WiPose system, the first 3D human pose construction framework using commercial Wi-Fi devices, which can also help us to see through the obstacles. Let's first watch a demo of our system.
3, 2, 1, go!
As you can see, in this work, we reconstructed the 3D human skeleton from the Wi-Fi signals collected by distributed antennas placed at different locations, even though the human subject is behind the wooden screen. So potentially, our WiPose system can enable a new generation of applications by supporting more sophisticated interactions between humans and their physical surroundings. This application includes the smart home, virtual reality, elderly monitoring with little privacy issue, fire rescue, gesture control, and no checkout shopping. Next, let's look into the details of our WiPose system. First, let's take an overview of WiPose. During the data collection process, we use one transmitter and several distributed receiving antennas to collect the Wi-Fi CSI data. In addition, we also use VICON motion capture system to generate the ground truth 3D skeleton of the subject. Then, we pre-process the collected CSI data, including denoising, transformation, and segmentation, to get an appropriate form of input. Finally, we feed the input into a novel neural network to generate the 3D skeleton of the subject. To achieve this goal, we have to address three challenges. The generated posture should be realistic looking. The synthesized movement should be smooth, and the model should be able to reconstruct human posture from the Wi-Fi signals collected from different subjects in different environments. An intuitive solution is to directly and independently estimate the position of each joint from CSI data. However, in this way, the generated skeleton does not necessarily keep the relationship among joints. As a result, the constructed skeleton may not look realistic. Look at these examples. The generated skeleton may contain unrealistically long or short limbs. After analyzing this problem, we gain some insights. First, after connecting the joints, we can represent the human skeleton as a tree with nodes to be the joints and edges to be the body segments. Second, in 3D space, we know that the bone length of the human does not change, so we can treat the body segments of the human as an individual rigid bodies. Under these two conditions, to infer the position of each joint, we only need to estimate the rotation of its associated body segments, which is its parent joint. Next, let's take the movement of an arm as an example. In this example, the shoulder is the parent joint of the elbow, which is also the parent joint of the wrist. Assume there are the initial position of the joints. The movement of the arm can be decomposed into two rotations. The first is to rotate the elbow around the shoulder. The second is to rotate the wrist around the elbow. In this way, we can generate all the movements of the arms as long as we know the rotation of the joints marked with the red curves. Similarly, to generate a skeleton from the whole human body, we recursively rotate the human skeleton tree from the root to the leaves. This process is called forward kinematics. Now, we introduce our proposed neural network, WiPose. We first transform the CSI data collected by all antennas into a sequence of input data. Then, we employ a stack of convolutional neural network to extract spatial features. After that, we use recurrent neural networks, specifically the LSTMs, to capture the temporal dependencies between the consecutive data samples. The last and ultimate part of our neural network is to utilize the forward kinematics layer to learn the rotation of the joints and apply them to a given initial joint to generate the desired posture. We propose three loss functions to train our model. They are the position loss, the smooth loss, and the rotation loss. As discussed previously, one challenge we will face when deploying the skeleton construction system in real world is to make it adapt to new environments and subjects. Our framework WiPose can improve the cross-domain generalization in two ways. The first is to learn cross-subject feature. Our WiPose framework encodes the skeletal structure of the subjects in the model, which makes the network learn the rotation of the joints. This feature is independent of skeletal structure of the subject. Secondly, we extract environment-independent inputs from the raw CSI data. From CSI data, we can obtain 3D velocity profile, which captures the power distribution of different velocities using the Doppler effect. The 3D velocity profile naturally can separate the posture-specific features from the ambient objects whose velocities are zero. Our Wi-Fi testbed consists of one laptop and three desktops with Linux CSI tool. Each computer is equipped with Intel 5300 NIC connected with three antennas. We use the laptop as the transmitter and active one antenna of it. We treat each antenna on the desktops as one receiver and place them at different locations. All devices work in the monitor mode and work in the same channel. The transmitter broadcasts the packets at a rate of 1000 Hz. We use the VICON motion capture system to generate the ground truth skeleton and train our proposed deep learning model with them. Our VICON system consists of 21 infrared cameras. We place 17 pole marks on each subject, representing the human skeleton, which can be captured by the VICON cameras. The VICON system can estimate each marker's position in 3D space with the estimation error less than 2 millimeters. We employ totally 10 volunteers and ask them to do 16 typical daily life activities. We compare our proposed WiPose with the IFPose 3D, which is a state-of-the-art deep learning model for 3D human skeleton construction from FMCW-based RF signal. It independently estimates the position of individual joints without explicitly enforcing the physical relationship among them. We use CSI as well as a 3D velocity profile as the input data of both approaches. As for the performance measurement, we use the average joint localization error, which is defined as the average Euclidean distance between the predicted joints locations and the ground truths. The second and the fourth rows are the result of our method, while the first and the third rows are those of the baseline. The results show that our framework performs much better than the baseline. The picture shows some examples of the constructed 3D skeletons. The result of IFPose 3D and our WiPose are the third and the fourth figures, respectively. From the picture, we can see that the 3D skeleton constructed by our framework is almost the same as the ground truth, while that of the baseline has distorted limbs. Moreover, some joints of the baseline are not moving smoothly. In contrast, our proposed framework reconstructs the activity truthfully and smoothly. Next, we investigate the effect of the occlusion on the performance of our proposed WiPose framework. We place a wooden screen between the subjects and the receiving antenna as shown in the figure. In this experiment, we collect the CS data for 6 of the employed 10 subjects. We also report the average joint localization error for this scenario. We found that results in the table are close to those in the basic scenario, which means WiPose is robust and it can still have good performance even there exists occlusions when collecting the CSI data. In order to evaluate the performance of our proposed WiPose framework across different environments, we evaluate our model on 3 scenarios unseen during the training process. Specifically, we train the model using the CSI data collected from the basic scenario, but test the model in 3 simulated scenarios. When the subject is occluded by the wooden screen, when the room is furnished with desks and chairs, and when the locations of the antennas are randomly assigned. The table shows the overall joint localization error for these 3 scenarios. We can see that in most cases, the model trained with 3D VP performs better than the models trained with CSI. This confirms the advantage of using this environment-independent feature. Moreover, after switching from CSI to 3D VP, our model gains more improvement than the baseline, which means that our model can make better use of the environment-independent feature than the baseline. In addition to the cross-environment setting, we also evaluate the performance of our proposed WiPose framework across different subjects. Specifically, we select 2 subjects with short stature as the testing set, and the other 8 subjects are put in the training set. In this way, the testing set is quite biased. The overall joint localization error in the table demonstrates that our framework performs better than the baseline in this biased setting. To summarize, in this work, we propose a framework named WiPose. It's the first 3D human pose construction using commercial Wi-Fi devices. WiPose is based on a novel deep learning model that encodes the prior knowledge of human skeleton into the construction process so that the skeletal structure of the human body is always satisfied. Finally, WiPose can improve the cross-domain generalization without collecting data in new domain. That's all for my presentation. Thank you very much.